In this third video, we're going to look at some of the remarkable consequences of the Cauchy-Riemann conditions that we derive by insisting on the existence of a complex derivative. Whereas the derivative of a real function is a local characteristic, in other words, it only provides information in the neighborhood about some point, we will see that the existence of a derivative for a complex function has much broader implications and tells things about the whole function. As a quick recap from the previous video, we saw how to derive the Cauchy-Riemann conditions relating the real and imaginary parts of a complex function. And we did that by insisting that the defining limit of the derivative does not depend on the direction of approach in the complex plane. We also tested a few functions using these Cauchy-Riemann conditions. After watching this video, you should be able to show that u and v satisfying the Cauchy-Riemann conditions also satisfy Laplace's equation. You should also be able to show that a differentiable complex function performs something called a conformal mapping. And lastly, you should be able to define what it means to say that a complex function is analytic, as well as what is meant by an entire function and a singularity. Let's get going.
We're going to begin by looking at some consequences of the Cauchy-Riemann conditions. In the previous video, we saw that these were necessary for the existence of a complex derivative. So the Cauchy-Riemann equations imply quite a bit about the complex function f of z is u plus I v. So I'm going to write down the Cauchy-Riemann equations again and label them so we can refer to them later. So we had that the first Cauchy-Riemann condition was that du by dx is dv by dy, and the second was that du by dy is minus dv by dx. Now recall that Laplace's equation, which appears in, for example, electrostatics and Poisson's equation, in 2 dimensions. It looks like this. You have the grad squared of some function, let's call it g, is the second derivative with respect to x plus the second derivative with respect to y. And for Poisson's equation, where the source term is 0, this is simply 0. With this in mind, let's consider taking derivatives. Consider taking derivatives of the Cauchy-Riemann equations at the top of the page. First of all, let's imagine taking the partial derivative with respect to x of that first equation. Well, the left-hand side is going to give us the second derivative of u with respect to x, and the right-hand side is going to give us d by dx of dv by dy, and that's a mixed partial derivative, which we can write like this. Next, let's take the partial derivative with respect to y of the second Cauchy-Riemann equation. So looking at the top of the page, the left-hand side is going to give us d squared u by dy squared, and the right-hand side is giving us d by dy of minus dv by dx, which again is a mixed partial derivative. Let's now consider adding these two lines together. So adding these together, we're going to get d squared u by dx squared from the top line, and then d squared u by dy squared from the second line. And we're now going to have d squared v by dx dy minus d squared v dy dx. Now partial derivatives commute, so these cancel and we get 0. So I'll note that partial derivatives commute. So these mixed partial derivatives on the right hand side of those equations cancel when we add together. I'll also note that if we repeat this procedure with derivatives the other way around, so in the first line we take the derivative with respect to y, and in the second we then take with respect to x. So repeat with derivatives the other way around. We get a similar result for v. So from this line here, which I've marked with an asterisk, we can essentially see that the function u satisfies the 2D Laplace equation. And performing the procedure again, we would also find that v satisfies the 2D Laplace equation. So I'm going to write that out in shorthand as grad squared u equals 0 and grad squared v equals 0. So u and v satisfy the 2D Laplace equation. Functions that satisfy the 2D Laplace equation are called harmonic functions. Examples of these are things like constants, polynomials, terms in multiples like x times y, and the exponential function. Harmonic functions are important in electrostatics, so I'll note that harmonic functions are important electrostatics. Fluid flow. So in fluid flow, harmonic potentials describe the flow of incompressible and rotation-free fluids. And harmonic functions are also important in heat flow. So solutions to the heat equation. Thanks to the Cauchy-Riemann equations, the real and imaginary parts of a complex function that is differentiable, in other words u and v, satisfy Laplace's equation. The Cauchy-Riemann conditions also imply another interesting property of u and v. We can also show that curves of constant u cross curves of constant v at right angles. Recall that we defined the gradient of some function as a vector where in 2 dimensions the entries are the derivative with respect to x and the derivative with respect to y. And what this means is we might have some curve of constant f, and at every point the gradient provides us with a vector that points at right angles to the curve of constant f. Now observe what happens if we take the gradient of u and take the dot product with the gradient of v. This is dxu, dyu, dotted with dxv, dyv. Multiplying this out, we get dxu, dxv, plus dyu, dyv. Now we're going to replace the second term in each of these products using the Cauchy-Riemann equations. And this will give us dxu times minus dyu plus dyu times dxu. And these terms cancel. We get 0. So we get 0 when f equals u plus iv satisfies Cauchy-Riemann. At the top of the page, we noted that the gradient of f is a vector perpendicular to curves of constant f. Now consider what we've just shown means. This means that because the gradient of u, gradient of v is 0, the vectors gradient of u and gradient of v are perpendicular. Therefore, curves of constant u and of constant v are perpendicular. And this is a very interesting property of the complex function. We say that f of z performs something called a conformal mapping. A conformal mapping means that the angles between lines of constant x and y in the input to the function are preserved between lines of constant u and v in the output of the function. I'll write that down. Curves of constant x and y are perpendicular. Therefore, curves of constant u and v are perpendicular. And for more information on conformal mappings, I point you to the book in the resource list on Blackboard, Riley, Hobson and Bentz, chapter 20, page 730 for more information. So Riley, Hobson and Bentz, chapter 20, page 730 for more info. What does an example of this look like in practice? Let's consider f of z is ln of z, which is ln, if we write z in modulus argument form, of r e to the I theta. If for now we assume that theta takes on its principal value between 0 and 2 pi, then we can write the logarithm of the product as the sum of the logarithms. We get ln of r plus I theta. We can therefore identify the real part of this function, u as ln r, and the imaginary part simply as theta. What does this look like in the complex plane? We've got our real and imaginary axes. And I'm first going to draw some curves of constant u. Now, curves of constant u, which is given by the logarithm of r, are going to be curves of constant r in the complex plane. In other words, constant radius circles. So we might have a circle with this radius, and we can do another one, slightly bigger. So these are curves where u is constant, and in this case that means constant radius, so a circle. On the other hand, lines of constant v are lines of constant theta, so constant angle in the complex plane. These are just lines radiating from the origin. I'll note v equals constant, which equals some fixed angle theta naught. And crucially, what we note is that these curves intersect at right angles. As another example that I'd encourage you to try yourself, try f of z equals z squared. If you manage to find u and v, you can then plot curves where they're constant, and again you'll find that they intersect at right angles. We've looked at the Cauchy-Riemann conditions for the existence of a complex derivative. We're now going to look at some other important terminology, namely that of analyticity of a complex function. If a complex function f of z is single valued and differentiable, in other words, it satisfies Cauchy-Riemann, in some region of the complex plane, we say it is analytic in that region. This is a very important definition, so I'll highlight it by underlining the important word. You should learn this definition. Other words used for analytic are regular and holomorphic. So if a complex function f of z is single valued and differentiable in some region of the complex plane, we say it is analytic in that region. It's important to note that it has to be in some region of the complex plane. So for example, analyticity at a point requires that Cauchy-Riemann holds in some region containing the point. I'll write that down as well to make it absolutely clear. So note analyticity at a point requires Cauchy-Riemann hold in some region containing the point. For example, f of z is mod z squared. Only satisfies Cauchy-Riemann at the origin. Because it only satisfies Cauchy-Riemann at a single isolated point, this function is not analytic. If a complex function f of z is analytic everywhere in the finite complex plane, in other words, ignoring the point z equals infinity, then f of z is called an entire function. And again, that's important, so I'm going to underline it in red. Some examples of entire functions, and we will later look at how you can tell if a function is entire. Examples are polynomials, the exponential function, and trigonometric functions, like sine and cos. A last point of terminology: points where the function fails to be analytic are called singularities or singular points. I'll underline those keywords as well. So, for example, if the derivative df by dz does not exist at the point z0, then the function is not differentiable at that point, and therefore f of z, according to our definition, is not analytic there. We will see that singularities of functions have amazing consequences when we come to complex integration later on in the course. We'll quickly look at a couple of examples to look at how to check for analyticity. So, examples. In the first case, let's consider f of z is 1 over z. We can write that as 1 over x plus iy. Now, by multiplying the top and bottom by z star, we can write this as x over x squared plus y squared, and then minus I y over x squared plus y squared, where we identify the first bit as our function u, and the second bit is giving our function v. Now, looking at the Cauchy-Riemann relations, the first one is that dxu is dyv, and you can plug these in yourself. The first one gives us minus x squared plus y squared over x squared plus y squared squared, and the right hand side gives us the same thing, minus x squared plus y squared over x squared plus y squared squared. And so this Cauchy-Riemann condition holds as long as the denominator does not equal 0. So z does not equal 0. For the second Cauchy-Riemann condition, we want that dyu is minus dxv. And again, we find that this holds as long as z does not equal 0. Therefore, we say that the function f of z is 1 over z is analytic except at z equals 0, where there's a singularity. As a next example, let's look at f of z is the complex conjugate of z. The real part is x, the imaginary part is minus y. The first Cauchy-Riemann relation from above is dxu equals dyv. Well, du by dx is 1, and dv by dy is going to give us minus 1. So this first condition does not hold. And we therefore can say immediately that the complex conjugate function is not analytic anywhere in the complex plane. So despite being continuous, the function z star is nowhere differentiable. I'll finally note that in general, complex functions that fail to be analytic are either multi-valued. We'll see how to correct for this in the next topic. So in general, complex functions that fail to be analytic are either multi-valued, which is not allowed by our definition. They are functions of the complex conjugate of z, or they are singular at isolated points. That's the end of this third video. As a recap, we saw that the Cauchy-Riemann relations mean that u and v satisfy the 2D Laplace equation, and they are therefore harmonic functions. We noted that some complex function f of z satisfying the Cauchy-Riemann conditions performs a conformal mapping between input and output. And we ended by looking at the definition of analyticity of a complex function, and what it means for a function to be entire. And lastly, we also considered singularities as points where analyticity fails. The take-home message of this video is that differentiability of complex functions is a much stronger condition than for real functions, and it has global consequences for complex functions as opposed to local consequences for real functions. Thanks for listening, and next up is the fourth video of topic 3.